Hello, good morning, everyone. Today I'll present our research focused on the temperature and the strain rate dependence of the mechanical response of polymeric syntactic forms. Firstly, I'll give a brief introduction about the polymeric syntactic forms. Then I'll describe the experimental methodology we used for investigation. After that, the mechanical response under tension and compression uniaxial loading for the polymeric syntactic forms will be present. I'll also compare the temperature and the strain rate dependence of the mechanical behaviors of the polymeric syntactic forms. Finally, I'll summarize our research and propose the field towards further investigation. The polymeric syntactic form are composed by a polymer matrix filled by hollow or solid particles. The dispersion of hollow particles distinctly enhance the specific strength and specific modulus without significant increase of density. Due to the advantages of the polymeric syntactic forms like the low density, low moisture absorption, the relatively high specific strength and stiffness, the heat isolation ability, and the polymeric syntactic forms are now used for the submarine, automotive, and aerospace applications, which subjected to a range of temperature and strain rate conditions. These SEM photos shown on the screen illustrate the microstructure of the failure surface of the polymeric syntactic forms under the quasi-static tension. The left one shows the microstructure of the nylon syntactic form. The middle one shows the microstructure of the epoxy syntactic form, and the right one shows the microstructure of the polyurethane syntactic form. It can be found that for the nylon and the polyurethane syntactic form, they are filled in the ductile manner, while for the epoxy syntactic form, it filled in the brittle manner. For all these three kinds of forms, the failure of the fracture of the hollow glass microspheres in perpendicular to the tension direction, but under compression, the failure of the hollow glass microspheres will be in parallel to the loading direction. There are two objectives. First, the physical and mechanical behaviors of the polymeric syntactic forms are highly sensitive to the temperature variations. And the second, the dynamic response of polymeric syntactic forms is significantly affected by the strain rate. There are three materials we chosen for investigation, which are the ductile nylon syntactic forms, the brittle epoxy syntactic form, and the rubbery polyurethane syntactic form. These three forms are all filled by the thin wall hollow glass microspheres with around 50% volume fraction. But the property of these matrices are widely different, which will represent the different types of polymeric syntactic forms. We have studied the strain rate dependent, the temperature dependent, and the loading mode dependent of these polymeric syntactic forms. So the experiments were conducted at the strain rate ranges from 10 to -3 per second to 10 to 3 per second, and the temperature and at temperatures ranged from -25 degree to 100 degree, and the experiments are all conducted under compression and tension loadings, respectively. At least three repetitions have been conducted for each experimental configurations to reduce the effect of random error and ensure the repeatability of the experimental results. The figures shows here illustrates the specimen configuration we've used for investigation. The cylindrical specimen with 5 millimeter diameter and 2.5 millimeter gauge length have been used for compressive characterization, while the dog bone specimen with threads at both ends of the specimen and with the gauge length of 8 millimeter length and 3 millimeter diameter have been used for the tensile characterization. For the quasi-static experimental apparatus, including these following equipments, and has been conducted at strain rate of 0.001 per second. Okay. The split Hopkinson pressure bar apparatus and the split Hopkinson tensile bar apparatus have been used for the high rate compression and tension characterization respectively. All the, sorry, can I play the all the experiment, oh, this video is not that clear. It shows the experimental setup for our high rate experiments, which including the split Hopkinson bar apparatus, the environmental chamber with the controller, the liquid nitrogen dewar, and a high-speed camera. The high rate experiment, the high rate compression experiment was conducted at the strain rate at magnitude of 10 to 3 per second, but the high rate tension experiment was conducted at the strain rate ranged from 30 per second to 50 per second because we have to achieve the dynamic equilibrium for our high rate test, and it's harder to achieve the dynamic equilibrium for these kind of forms at under tension, so the lower strain rate were chosen. For the split Hopkinson bar analysis, I think you guys may be very familiar with that as the time is limited, so I just skip this part. The dynamic equilibrium conditions are achieved once the stress pulse reverberates approximately 3 times within the specimens. The materials characterized by a low ratio between stiffness and density needs a longer time to achieve dynamic equilibrium. It can the left photos show the specimen with the dynamic equilibrium, while the right photos shows the specimen without the dynamic equilibrium. The dynamic equilibrium conditions can be improved by reduce the aspect ratio of the specimen design or use the pulse shaping techniques. These 3 plots plot the typical forces measured in the incident bar and the transmit bar under tension loading or at strain rate of 50 per second and at room temperature. It can be found that the dynamic equilibrium had been achieved at the initial elastic deformation stage, which validates that our experimental results are valid. Okay, these plots show the mechanical response of the investigated polymeric syntactic forms under quasi-static and high-rate compression. It can be found that for the nylon and polyresin syntactic forms, their deformation are corresponding to the classic compressive deformation of the elastic, plastic, cellulose solids, which consist of the 3 stages: the linear elastic stage, the plateau stage, and the densification stage. While for the epoxy syntactic form, it's break in the brittle manner, And for all these three kinds of forms, it can be observed that these mechanical responses are all highly dependent on the temperature and the strain rate change. These plots shows mechanical responses of the polymeric syntactic forms under high rate and quasi-static tension at various temperatures. It can be found that for this kind of tension deformation, it happens like faster and failure at lower stress compared with compression. But all these deformation are all dependent on, or are also dependent on the temperature and strain rate change. From our experiment, it has been found that there is temperature and strain rate dependence of the strands. With this scatter plot, it can be found that the compressive and the tensile strands increase with the increase of the test strain rate and decrease of the test temperature. The densification strain is one of the most important property of the cellular solids, which indicates that where the cellular solids start to densification, and which means that there is cell wall interaction of these solids. These increase the densification increase the compressive resistance of the cellular solids, but there is ambiguity and uncertainty of the definition of the of where at which strain this densification occurs. Here we use strain energy dissipation efficiency curves to define the densification strain. When the efficiency, then where is the maximum efficiency, then there is where at this strain the densification occurs, which gives a unique and constant result. It can be found that for the nylon and polyresin syntactic forms, regardless the temperature and strain rate change, they gives the densification strain are almost constant. Then this constant densification strain gives increase of the strain energy dissipation efficiency dissipation for the densification, along with the increase of the test strain rate and decrease of the test temperature. So in conclusion, the pronounced test temperature and strain rate dependence of the polymeric syntactic forms, compressive and tensile responses, were both observed during the experiments. The strain rate and temperature sensitivity are different for the examined syntactic form due to the difference of these three matrix. So in the future, we will discover the property of the syntactic form under the torsional and combined tension torsional loadings, and also we will also characterize the sensitivities of the moisture absorption effect on the polymeric syntactic forms. Many thanks for listening. Any questions?